Good morning, everyone. Hope you're all doing well. I'm going to give people a minute or two to trickle in, and then we're going to get started right away. Uh, as you know, just for an intro, today is going to be all about trig equations and identities. So we're going to talk briefly about the unit circle, where the functions sine and cosine come from, how we can understand the key values of sine and cosine, and then we're going to talk about some basic trig identities, so standard level identities. And then in about an hour, we'll get to the HL content, which includes more advanced trig functions like the reciprocal trig functions and the inverse trig functions, and more advanced identities. Okay, so I'm just going to set up uh, the screen share and we will get going. Okay, we're ready to go. So let's think about sine and cosine on the unit circle. So I want you to imagine that you're watching a dot travel around a circle of radius 1, and you can see that in the picture below. And this special circle, which has a radius of exactly 1 and is centered at the origin, is called the unit circle. And as this dot moves around the circle, the angle that it creates from the positive x-axis, so this angle here, determines two important values. It determines the horizontal position of the point, and it determines the vertical position, or the y-coordinate of the point. And it determines those using cosine and sine. So the x-coordinate of the point is going to be cosine theta, and the y-coordinate of the point is going to be sine theta. All right? So cosine and sine are respectively, the base and height of a right angled triangle with a hypotenuse of 1. All right, so if we remember, if I just make this stop for a second, we remember that our first definitions of sine and cosine were as trigonometric ratios, so SOHCAHTOA, and we said that sine was the opposite over the hypotenuse. We said sine of theta is equal to opposite over hypotenuse. So in this triangle where I have theta here, the opposite is simply the y coordinate, and the hypotenuse has a length of 1 because I'm in a unit circle, which means that sine theta gives me y. In a similar way, cosine theta was the adjacent over the hypotenuse, and the adjacent here is the x-coordinate of this point, and hypotenuse is still 1, so this is just x. And that is why sine and cosine give me the coordinates of the points on the unit circle. Okay, so if you trace out the values of sine and cosine with theta as the argument on the x-axis, you will find sinusoidal graphs. And we'll talk more about this in a second, but if I open this up, you see basically that as this point goes around, this blue line over here, which is it's the graph of sine actually, is going to have the same height as the point, okay? And as it goes around, what I'm plotting on the x-axis here is the angle theta. All right, so this is how you can see the connection between the unit circle and the graphs of sine and cosine, all right? Now, we have some key values on the unit circle that we need to remember. And I'm not going to sort of go through the tedious process of showing you how you can find these values, but it's actually not too bad. You can use triangles and things that we know about triangles. You can make isosceles triangles, and you can make right triangles. There are pretty easy ways to find these values, kind of from nowhere. But for today, I'm just going to assume that we've done that, and we know the following sine and cosine values. And this is for theta in radians, by the way. Most of the time we'll be doing trig with radians, but not exclusively. So if I have 0 radians, maybe I'll draw a circle next to this so we can understand these values as I'm saying them. If I have a unit circle, all right, then 0 radians corresponds to this point here. The angle it makes is 0, and the height of that point is 0, okay? And the base there, the x-coordinate, is 1, because the unit circle has a radius of 1, and I can tell that this point is just along the radius on the x-axis, okay? I can also tell that if I set the point, or if I go to the angle pi over 6, oh, hang on. And pi over 6, by the way, if you think about it, pi over 6 if you divide that by 2 pi, you find that pi over 6 is compared to the full circle, 1 over 6 over 2, it's 1/12 of the full circle. Okay, so 1/12, it's a third of a quarter, and this is a quarter. So pi over 6 is going to be here, roughly. Okay, and I can tell approximately what this value is, but I'm also just going to tell you that it is exactly 1/2. The y coordinate, or the value of sine pi over 6, is exactly 1/2. And the x coordinate is √3 over 2. Okay? Pi over 4 is going to be here. It's going to be a quarter of the way between 0 and pi over 2. Sorry, halfway between 0 and pi over 2, or a quarter of the way between 0 and pi. And it's going to have both an x and a y coordinate of √2 over 2. And that's because it's this special angle 45 degrees, which is kind of exactly a quarter of the unit circle. So it's going to have the same x and y. Okay? So that is pi over 4. And then pi over 3 is going to be up here. It's kind of the reflection of the point pi over 6 in the line y is equal to x. And it's going to have an x coordinate of √3 over 2, and y coordinate of √3 over 2, and an x coordinate of 1 over 2. And then finally, pi over 2 simply has a height of 1, so sine theta equals 1, and a x coordinate of 0. One thing I want you to notice here is that if I take the squares of each of the values in this column, I do 0 squared plus 1 squared, I get 1. If I do 1 over 2 squared plus √3 over 2 squared, I get 1 over 4 plus 3 over 4, I get 1. Okay? And I'm actually always going to get 1. And you can think about that because whatever triangle I decide to draw in the unit circle, I know that it has a hypotenuse of length 1. And I know that this is cos theta, the base, and this is sine theta. So simply applying Pythagoras tells me that sin squared theta plus cos squared theta is always going to be equal to 1. Okay? So that's an important property to remember. Now, when it comes to trying to memorize trig values, because I know a lot of students struggle to keep these in mind, because you have kind of 1 over 2, √2 over 2, √3 over 2, I like to think about each of the values as the square root of, for the first one, 0 over 4, and that would give me 0. Then the square root of 1 over 4, which is the same as 1 over 2. The square root of 2 over 4, which gives me √2 over 2. Square root of 3 over 4, and square root of 4 over 4. This makes it a lot easier to see the pattern, right? Which is that I have 0, 1, 2, 3, 4, all divided by 4 under the square root, and the opposite for cosine. We start at 4 over 4 square root, then 3 over 4, then 2 over 4, then 1 over 4. That might help you to memorize these values instead of these kind of somewhat random-looking square roots that you have in this table. All right, now we also have some important symmetry properties in the unit circle, okay? For instance, because the y coordinate is going to be the same if I reflect it across the x-axis, if I take the angle pi minus theta and the angle theta, I notice that they have the same value of sine. They have the same height, okay? And that's because the angle between the negative x-axis and the positive x-axis is pi. And so these angles complement and therefore have the same sine value. We notice that they don't have the same cosine value. In fact, they have the opposite cosine values. They're the negatives of each other. Okay. That also allows us to start thinking about this notion of quadrants, right? So the unit circle can be divided into quadrants based on the sign, whether the positivity or negativity of cosine and sine. And these correspond to the 4 quadrants produced by the intersections of the x and y axis. So you'll see here that sine theta was positive, sine theta is positive. Well, I'm not going to, the labels will tell you, but now sine theta and cos theta are both negative in quadrant 3. Point's going to come around now, and all of a sudden, cos theta is positive and sine theta is negative. And then now they're both positive again. Okay, so sine theta, remember, it's all about the y direction, so it's going to be positive up here and negative down here. And cos theta is going to be positive over here and negative over here, which means that in quadrant 1, I have plus plus. They're both positive. Quadrant 2, I have sine positive, cosine negative. Quadrant 3, I have both negative, and quadrant 4, I have sine negative, cos positive. All right. Okay, now this is a very important idea, but periodicity basically means that if I add 2 pi to any angle, or in fact any even multiple, any integer multiple of 2 pi, I'm going to get back to the same place. And you can see that with this like relatively simple visual. All that's happening is I'm starting with a point, and I'm going one full rotation around, and I'm arriving back to the point. And I can keep doing that forever. But the point is, if the whole circle is an angle of 2 pi, then adding 2 pi takes me back to exactly the same place. And so the sine and cosine are not going to change. So cosine of theta plus 2k pi for any integer k is the same as cos theta. And similarly for sine theta plus 2k pi. This is going to be really interesting, like a really useful property when you're trying to find the sine and cosine of angles that are bigger than 2 pi. Like if you wanted to find sine of 2000 0.5 pi, okay? Well, that's the same thing as 2000 pi plus 0.5 pi. But 2000 pi is a perfect multiple of 2 pi, sorry. So that means I've done, in this case, 1,000 loops around the circle, and then I've done 0.5 pi. So this is actually the same as 0.5 pi. All right, and 0.5 pi is pi over 2, and that is corresponds to this point up here on the unit circle, and so sine theta is going to be 1 here. All right, clear my screen and continue. All right, so now I want you guys to do this exercise where you're going to drag this point to roughly the right place on the unit circle, okay? And I'm going to give you about a minute to do that, all right? All right, I think that's enough time. So let's think about this. I have negative 229 pi over 6, which is pretty big. It's, at least 180 over. So it's bigger than, it's less than negative 30 pi, because 180 over 6 is 30. But what I can do is remember that because of periodicity, any multiple of 2 pi that I add is actually not going to change anything. So if I'm adding 2k pi, if I'm doing that over 6, it's the same as adding 6k pi over 6. Sorry, what am I saying? Same as adding 12k pi over 6. All right, 12k pi over 6. And I'm going to add that to this as many times as I need to get an angle that I can recognize. Okay? So if I added it once, let's say, I would have, I would go from negative 229 pi over 6, and then I would be at negative 217 pi over 6, blah, blah, blah. But I can go a bit faster, and I can add a multiple. I can just add like k is equal to 10. Okay, I can add a lot of angle at once. So if I add 120 pi over 6, then I'm going to have 80 plus 17 is negative 97 pi over 6. So I'm still not there. Okay, 97. If I add another 60 pi over 6, because that's a multiple of 12, I can add another 60 pi, and that brings me to negative 37 pi over 6. And now I'm going to add another 36 pi over 6, and that's going to bring me to negative pi over 6. All right, and negative pi over 6, if I wanted to add one more time 2 pi or 12 pi over 6, I would get 11 pi over 6 if the positive angles make more sense to you. But 11 pi over 6 or negative pi over 6 is somewhere about here. Okay. Perfect. Let's continue. So another type of symmetry that you have to remember, and it's maybe less important than the other type of symmetry about sine, but if I have sine of theta and I add pi, okay, so adding pi means going to the other side of the unit circle, then sine is going to have the opposite value, and also cosine is going to have the opposite value. And that's because adding pi, you can think of as just going to the other side of the unit circle, because pi is half a circle, so I'm going halfway around the circle, and then I'm on the opposite side. It's like I've taken the reflection of the points cos theta, sine theta, and now I have negative sine theta and negative cos theta. All right? Similarly, we have a symmetry about the x-axis, right? This is similar to the kind of symmetry we had for sine theta about the y-axis, but if I have the angle theta and negative theta, I notice that the value of cosine is going to be the same. They're going to give me the same x-coordinate. It's not true for sine. Sine of negative theta is negative sine theta. I can tell that they have opposite y-coordinates, but they have the same x-coordinate. All of these together allow us to relate angles between quadrants. All right, so once you know sine and cosine for the first quadrant, you can use all of these rules to turn an angle that you're looking for into an angle in a specific in the first quadrant. Okay, so let's do a couple examples. If I have cosine of 31 pi over 6, I can first rewrite that as cosine of 30 pi over 6, which is 5 pi, plus pi over 6. All right, and then any multiple of 2 pi does nothing, so I can subtract it out. So I subtract out 4 pi, and I'm left with cos of pi plus pi over 6. And we just saw that adding pi to an angle flips the cosine to negative. So cos of pi plus pi over 6 is negative cos of pi over 6. So that's going to be negative square root 3 over 2. All right. Let's do a similar example for sine. If I have 223 pi over 4, I can write that as 220 pi over 4 plus 3 pi over 4, and 220 over 4 is just 55 pi. Again, I can subtract out any multiple of 2 pi, so I'm going to subtract out 54 pi. That's going to bring me to sine of pi plus 3 pi over 4, and similarly, remember, we have sine of theta plus pi is equal to negative sine of theta, so sine of pi plus 3 pi over 4 is minus sine of 3 pi over 4. And 3 pi over 4, remember, is gives a sine of root 2 over 2. And so the answer is negative root 2 over 2. Checking for questions. No questions. Okay. All right, it's your turn. I'm going to give you a minute to do both of these. Okay, that's time. Let's go over this. So I have cosine of 113 pi over 3. And I'm going to have to reduce that down into an angle that's on the unit circle and use the laws of symmetry to find the value. Okay, so I'm going to start by recognizing that 113 pi over 3 is outside the unit circle. So I'm going to have to subtract out 2k pi until I get an angle that's on the unit circle. All right. So I'm going to start, because 2k pi, by the way, is, if I put that over 3, it's negative 6k pi over 3. So I'm subtracting multiples of 6 pi from 6 pi over 3, or 6 pi from 113, okay? So I'm going to start by subtracting out 60 pi, so I'm going to go 113 pi over 6. I'm going to subtract out 60 pi, and that's going to give me 53 pi over 6, okay? Then I can subtract out another 30 pi. That gives me 23 pi over 6. And if I subtract out now another 18 pi, then I get 5 pi over, and I don't know why it suddenly became over 6. This was supposed to be over 3. Excuse me, 5 pi over 3, over 3, over 3, and 5 pi over 3. And 5 pi over 3, I can think of as, well, I can think of that as cosine of 2 pi minus pi over 3, or in other words, cosine of negative pi over 3. And I know that the cosine of negative an angle is the same as cosine of the angle, so this is cosine of pi over 3. And we know that that is 1/2. Okay? It often helps to visualize these with a unit circle, to think about where these angles are, and actually sketch on the side of your page when you're doing your work a little unit circle, and try and think about these angles and where they are, because if you get 5 pi over 3, you'll realize, oh, okay, that's here, and it makes you more likely to remember how that relates to pi over 3. Part B, we're looking for sine of negative 59 pi over 4. All right, so 59 pi over 4, I'm going to add multiples of 2 pi, which is the same as adding 8 pi over 4. And I'm going to just start by adding 8 times that, because 59 is pretty close to 64. So I'm going to do negative 59 pi over 4, and I'm going to turn that into 5 pi over 4, 5 pi over 4, which is the same as pi plus pi over 4. So the sine of negative 59 pi over 4 is the same as sine of pi plus pi over 4. And we know that adding pi to an angle changes the sign, so it's negative sine of pi over 4. And we know that sine of pi over 4 is root 2 over 2. So the answer here is negative root 2 over 2. The last thing about the unit circle that I want you to know is that you can think of the tangent, or tan, sorry, not tangent, tan as the slope in the unit circle. So we introduced this new function tan, which is sine theta divided by cos theta. And sine and cos are, if you remember, the y and x coordinates of the point on the unit circle. And so if I do the y coordinate divided by the x coordinate, I get the slope of the line between the origin and the point cos theta sine theta. All right? Now, this interpretation of slope is not always going to be relevant. Most of the time, you can just think of tan as like a function that gives you a number. But it is useful sometimes for finding angles when you know slopes of lines, and you're told to find the angle that a line forms with the x-axis or something like that. Okay? But let's do an example. If I'm looking for tan of 17 pi over 6, I can use the same rules for periodicity, right? Because if I add 2 pi and sine and cosine don't change, then tan can't change because neither sine nor cosine have changed. All right, so I add 2 pi, or I remove out 2 pi, so I take out 12 pi over 6, and I'm left with tan of 5 pi over 6. And according to my definition up here, that's sine of 5 pi over 6 divided by cos of 5 pi over 6. And both of those values of sine and cosine I can find using the same procedure we did earlier for sort of using the symmetries to find the values of sine and cos. And I would find 1 over 2 for sine 5 pi over 6, and negative root 3 over 2 for cos of 5 pi over 6. And if I simplify that down, I get negative 1 over root 3. And if you want to rationalize that, it's equal to negative root 3 over 3. All right, let's continue. One more rule, we talked about this already, but it's important just to remind you because it's the most influential trig identity that is going to be on your exams. It's the one that is going to show up the most. It's going to show up everywhere. And so you need to understand this one deeply and have it so ingrained in your brain that you never forget it. So remember, if sine and cosine are the x and y coordinates on the unit circle, well, the unit circle has a radius of 1, and therefore, if I take cos of theta and sine of theta, they're in a right angled triangle with a hypotenuse of 1, and so sin squared plus cos squared is equal to 1. So for example, if I know that I have cos of theta is equal to negative 3 over 5, find sine theta given that the angle is between pi and 2 pi. Okay, so let's try and draw out what I know in this example. I know the angle is between pi and 2 pi, so my angle is somewhere here. And I'm told that cosine is negative 3 over 5, so that's like, negative 0.6, and cosine is the x-coordinate, so I draw a line x is equal to negative 0.6, which means I'm somewhere here, okay? And if I connected that line to the origin, I still know that this is 1, and I know that this is negative 3 over 5, and the question is, what is this? Well, if I do sine squared plus cos squared is equal to 1, then sine squared theta plus minus 3 over 5 squared, and actually I have the working on the screen, so I don't need to actually write it out, is equal to 1. Then sine squared theta is equal to 1 minus 9 over 25, which gives me 16 over 25. If I take the square root of both sides, then I get plus or minus 4 over 5. Now, why is there no plus or minus in my final answer? Because of the angle that I was restricted to. I was told that theta was between 0 and pi. And in that interval, sine theta is negative because I'm below the x-axis, which means that sine theta has to be negative 4 over 5. Okay? And this is going to be tradition in any question where you have to find the value of sine or cosine given something else. If you use the Pythagorean identity, the IB is going to try and trip you up by giving you a specific domain so that only the positive or only the negative case is valid. And you have to pay very close attention to make sure you find the right one. Okay, so your turn. I'm going to give you a minute to do this example. Okay, let's go over the answer to this. So I'm going to be using the Pythagorean identity sin squared theta plus cos squared theta is equal to 1. And I'm going to plug in what I know, which is that sine theta is 4 over 5. So 4 over 5 squared plus cos squared theta is equal to 1. So 16 over 5, 16 over 25 plus cos squared theta is equal to 25 over 25, which means that cos squared theta is equal to, if I subtract 16 from 25, I get 9 over 25. So that means that cos of theta is equal to plus or minus, if I take the square root, 3 over 5. Now the question tells us that we are between pi over 2 and pi. So on the unit circle, that looks something like this. We are between here and here, so we're somewhere here. In other words, cosine is negative, so I must have this negative sign. And then I remember that tan of theta is equal to sine of theta over cos of theta. In other words, I know that sine of theta is 4 over 5, and that cos of theta is negative, negative 4 over 5, not 4 over 4. 4 over 5 and negative 3 over 5. This gives me, why do I keep writing 4? Negative 3 over 5 is equal to negative 4 over 3. Okay, that is my answer. Let me check for questions quickly. No, we're good. Perfect. I'm going to continue on now with trig functions. So I mentioned this a little bit before when I showed you the unit circle, but I can make a function using sine and theta, and I can generate its graph by imagining, as this point goes around the unit circle, taking all of its y-coordinates as it goes around and plotting them against, as on the x-axis, the angle that it's currently forming with the x-axis, okay? And it's a little bit hard to visualize how I get the cosine one, but basically I'm taking the x-coordinate and I'm making that the y-coordinate of the graph, right? Because when I draw the graph of a function, I draw y is equal to something. And because I want, the cosine gives me the x-coordinate of the point, it's a little bit weird to understand what's happening. But if you just remember that cosine, when the angle is 0, starts out at 1, then it decreases to 0, and then to minus 1, and then back to 0 and back up to 1. You'll notice that the graph is going to do the same thing. Starts at 1, goes down to 0, minus 1, 0, and back up to 1. And now we loop again, right? And the key thing to notice is that these functions are periodic, okay? Which means that after I get to 2 pi, they're going to repeat. So I get to 2 pi, and the blue curve is going to do the same. It's going to go up again and back down. And the orange curve, cosine, is going to do the same as well. It's going to just start going down again. And they're going to loop with the same pattern for all real numbers, all right? We also notice that they have a range of between minus 1 and 1. Cosine can never be bigger than 1 or smaller than minus 1, and the same for sine. And that's just a consequence of the fact that these values came from coordinates on the unit circle, right? Sine is the y-coordinate and cos is the x-coordinate. And if I'm on a circle and the radius is 1, I can never have one of the coordinates bigger than 1 because otherwise I'd be outside the circle, okay? And it's also important to notice, especially at the higher level, that the cosine function is kind of lagging behind the sine function, right? I noticed that the cosine function is always kind of copying what sine is doing, pi over 2 ahead of it. And I can write that as saying sine of x minus pi over 2 is the same as cos of x, okay? This is not in your formula booklet, and you don't need to memorize it per se. If it does show up in a question, the question will first kind of either have you show it or remind you of the fact in some subtle way. All right, that brings us to the notion of sinusoidal functions. And that sounds like a fancy word. It just means transformed sine and cosine functions. So I've moved it up, down, left, right, whatever it is, who knows. And the point is that we can use these functions to model a lot of phenomena in the real world. Okay, so I can use these to model tides or circular motion of various things. It's a very, very powerful function in terms of its applications. And so it shows up a lot in questions. And we're going to do an example in a minute now. But basically, I'm going to have a function of the form a times sine of b x plus c, all plus d, or similar but with cosine. And what you should notice is that by doing plus d, I move the center of the function, which was on the x-axis at y is equal to 0. I move it to y is equal to d. That's the midline of the new function. I also have this amplitude, which is the distance between the midline and the peak. It used to be 1, right? Because the maximum value was 1, but I multiplied by a, so now that amplitude is a. Okay? What else have I done? Well, by multiplying the inside by b, remember that's according to transformations, that is a horizontal stretch by scale factor 1 over b, okay? Which means that now the distance between two peaks, which used to be 2 pi, right, is now 2 pi divided by b, okay? And then this plus c just kind of shifts things left or right, but usually in IB questions, it's not actually going to be relevant, okay? It kind of just makes things annoyingly messy and doesn't really make anything more interesting, so it doesn't show up too often. But it just shifts things left to right. It's a horizontal translation. Okay, also the tan function, if I remember that tan is sine divided by cosine, then tan is going to have vertical asymptotes whenever cosine is equal to 0. Because if the denominator is 0, I have a vertical asymptote. All right? And also, I know that since tan of x plus pi is sine of x plus pi over cos of x plus pi, and adding pi to an angle means changing the sign of the sine and the cosine, then this becomes negative sine divided by negative cos, but the negatives will cancel and I get back tan, which means that the period of tan x is just pi. And when I say period, I mean how far, what's the smallest x I have to go across for the function to repeat its behavior again. So every time I go across by pi, I'm going to be at exactly the same place no matter where I started. Now that's also true, by the way. If I went 2 pi across, I could go all the way from here to here and do 2 pi, and I'd be in the same place. But that's not the period, because the smallest way I can do that is to go across by pi. So that's kind of just an important definitional thing. The period is the smallest value I can add to get back to the same place. Okay. That is trig functions. Now let's do a little example. I'm going to give you guys 4 minutes to try this on your own, and then I'm going to go over the solution, okay? All right, let's go over the solution here. So I have a wind turbine, and it's spinning here, isn't that cool? And it has a diameter of 16 meters, and it rotates clockwise at a constant speed of 1 revolution every 4 seconds. The blades are fixed on a shaft such that the tip of the blades are always at least 7 meters above the ground. Okay, and the point Q lies at the tip of one of the blades. All right, and thank God we have a picture, because that is a bit of a word soup. And now we're told that h is the height in meters of Q above the ground, and after t minutes, h is given by h of t is equal to a cos bt plus c. Okay, and part A wants us to show that Q starts at the highest possible point. So Q starts when t is equal to 0. So h of 0 is equal to a cos of 0 plus c. Okay? And cos of 0 is just 1, so this is going to be a plus c. A plus c. And a is bigger than 0. Okay? Since a is bigger than 0, then the maximum value of h of 0, of h of x, h of t even, h of t is going to be in the range negative a plus c up to a plus c. This is the, and I should put inclusive, this is the range of the function. And so when I'm at a plus c, that is the maximum. So a plus c, so h of 0, which is equal to a plus c, is the max. All right, and that is the answer to part A. So on part B, I'm trying to find the values of a, b, and c using the dimensions that I can see in the diagram. So the first thing I want to notice is that the minimum value of the height here is 7 meters. And since I have a diameter of 16 meters, the radius is going to be 8 meters. Okay, if that's 8 meters, then if I do 7 meters plus 8 meters, it means that this height here is 15 meters. And that is the center line, right? Q is oscillating in height around that line. This is the center line at y is equal to 15 meters. And that means that c is equal to 15.
because the midline is when the cosine goes to 0, and all I have left is c. So I have c is equal to 15. And then the amplitude A is just how far above and below that midline the point can reach. Okay, and we see that that's just the radius 8 meters. So A is equal to 8. Now the hard part of this question is figuring out what the value of B is. So let's just remember that if I have a function f of bx, okay, if I'm trying to sketch f of bx, that corresponds to a horizontal stretch by a factor, a scale factor of 1 over b. Remember, because a horizontal stretch goes in the opposite direction when I am multiplying the argument, okay? So normally cosine would have a period of 2 pi. Now, in this question, it has a period of 4 seconds. 4 seconds, there are 60 seconds in a minute. So the period of cosine of b times t is 1 over 15 minutes. Okay, 1 over 15. All right, what does that mean? It means that when I do 2 pi, which was the original period of the function, and I did my transformation, which corresponded to a scale factor, 1 over b, I got 1 over 15. And now I can solve for b. How am I going to do that? I'm going to bring b to the... Oh my god. I'm going to bring b to the other side. So I'm going to get... I'm going to multiply both sides by 15 and by b. So I'm going to get 15 times 2 pi is equal to b, which means that b is equal to 30 pi. And that is my answer.
Next. All right, now we're going to talk about trig equations. Okay, so the most basic kind of trig equation is solving basically in an inverse trig value. So instead of finding the value of sine for an angle, I can find the angle using what I know about sine. So let's say I know that sine theta is equal to a, okay? Since sine theta represents the y-coordinate of the points on the unit circle, then solving sine theta is equal to a is equivalent to drawing the line y is equal to a and finding the intersections of the unit circle with that point, with that line, sorry. And we notice that's almost always going to give me two solutions, except if I draw the line y is equal to 1 or a line that's outside the unit circle, which is going to have no solutions, okay? And this helps visualize all the possible solutions for sine theta is equal to a, okay? Now, the first solution, the one over here, is going to be sin negative 1 of a, or in this case, sin negative 1 of 1 over 2. But the second one, the complementary angle, is on the other side, and that's going to be pi minus the inverse sin of 1 over 2. Okay, so the two solutions are theta is equal to the inverse sin of a and pi minus the inverse sin of a. Now, I think it's more helpful to just think about these in the unit circle instead of inverse sine, because usually you won't have a calculator for these questions anyways. I know that sine of pi over 6 is 1 over 2, so I have one solution, which is pi over 6. And then I also know that sine is the same thing when I reflect it in the y-axis. So the angle over here, well, that's going to be pi minus 5 pi over 6, or sorry, pi minus pi over 6 gives me 5 pi over 6. That's how I think about that. Okay? So, similar story for solving the equation cos of theta is equal to a. Cos of theta represents the x-coordinate, so I draw a vertical line at x is equal to the value of a, and I find the intersections. And again, usually I'm going to have two, unless I have some special values. And this helps me visualize the possible solutions. So if I have cos theta is equal to a, I have cos negative 1 of a and 2 pi minus cos negative 1 of a. And it's 2 pi minus because the symmetry for cosine is that cos of 2 pi minus theta is equal to cos of theta. You can also write this as cos of minus theta is equal to cos of theta. It just depends on what the domain in the question is. If it says 0 is less than theta is less than 2 pi, then I can't have negative theta because that would be a negative number. Okay? Let's move on. Now, this is really tricky, but trigonometric solution domains. When you have a trig equation that you have to solve in IB, they will give you the interval of the value of theta. They'll say something like theta is between 0 and 2 pi, okay, in general. But sometimes they might say between 0 and pi over 3. It just depends. But typically it's going to be between 0 and 2 pi. Now, other times, the arguments of the trig equation might not simply be pi, but something like a times theta plus b. So, for example, you might be told that sine of 2 theta minus pi over 2 is equal to 1. And now what's inside the function is no longer theta, which makes it difficult because we're told the interval for theta. So theta is between 0 and 2 pi inclusive. All right. To solve these kinds of questions, it really helps to just say, okay, I'll let x or u or something be equal to 2 theta minus pi over 2. All right. Then I have the equation sine of x is equal to 1 over 2. And what I do is I immediately transform my interval. This is the way I approach these. I immediately change the interval to get an interval for x. So if theta has a minimum of 0, then x is going to have a minimum of 2 times 0 minus pi over 2. So that's going to be negative pi over 2. And theta has a maximum at 2 pi. So x is going to have a maximum at 2 times 2 pi, which is 4 pi, minus pi over 2 is 5 pi over 2. Okay? And that's really, really helpful because now I know that sine of x equals 1. On the unit circles, that corresponds to being up here, which means I'm up there, which means I have pi over 2 plus 2k pi. So I can do pi over 2 plus 2k pi. That's the values of x. And the plus 2k pi is just capturing the fact that I can go around the circle. I can do any full rotation around the circle. It's going to bring me back to the same point. Okay? So if I list out the first few positive and negative values here, I have, if I do pi over 2 minus 2 pi, I have negative 5 pi over 2. Then I have pi over 2. And then I have, I don't know why. Yeah, then I have 3 pi over 2. Then I have 7 pi over 2. And what I do then is I use the interval, which I found for x, to decide which of those would have been valid for theta. Okay? So these are the solutions for x. I have x is equal to negative pi over 2 and 3 pi over 2. And now I have to turn those back into solutions for theta, right? And I said x is equal to 2 theta minus pi over 2, which means that x plus pi over 2 is equal to theta. All right? And that means that the valid solutions are going to be, if I do that plus pi over 2, I get 0. So I get theta is equal to 0. Or if I do 3 pi over 2 plus pi over 2, I get 2 pi. I divide that by 2, I get pi. So theta is equal to 0 or pi. Those would be my final answers to this question. Okay, and if you find this changing of the interval confusing, it's also totally fine to leave it as an interval in terms of theta, and then at the end transform all of the solutions that you find, or maybe even just the general solution. I could turn that into theta is equal to same rule. I do x plus pi over 2 all divided by 2. That's going to give me pi plus 2k pi over 2, which is just going to give me pi over 2 plus k pi. But hang on, I think that is slightly wrong. Actually, these values are wrong. I don't know where I got those. That's supposed to be plus. I don't know how I got a minus sign there. Sorry. I got a minus sign because those are the values of theta. I actually already converted these back, which is why there was a bit of a confusion here. Okay, sorry. So these were values of theta and not of x. I had already done this step without showing you, which probably was bad, but okay. Now it's your turn. I'm going to give you probably a minute and a half for this one, maybe 2 minutes. Okay, let's go over the solution here, step by step. So I'm going to start by doing exactly what I did on the previous slide, which was to start by making the substitution x is equal to 3 theta minus pi over 2. And for the sake of showing you how it works, I'm not going to convert the solution domain. I'm going to do that at the end, okay? So I have cos of x is equal to 1 over 2. And the cos of x is equal to 1 over 2 when x is equal to pi over 3 or, plus 2k pi. I can add anything to that. Plus 2k pi. And sorry, I also have, there's a plus or minus here. I can have negative pi over 3 plus 2k pi. All right, those are the two values that I would find. And then if I reverse this to find theta, I would get something like x plus pi over 2 all over 3. What's that going to look like? It means that theta is going to be pi over 2 plus or minus pi over 3 plus 2k pi all over 3. And that is definitely a bit of a mess, okay? So I'm going to start with the case k is equal to 0, just to see what I would get. And I would get theta equals to either, I'd get pi over 2 plus or minus pi over 3 all over 3, all right? And pi over 2 plus pi over 3 is 5 pi over 6, and I divide that by 3, and I would get 5 pi over 18. And if I did pi over 2 minus pi over 3, I would get 3 pi over 6 minus 2 pi over 6 is pi over 6, and all divided by 3 would be pi over 18. Okay, so I have at least those two solutions because those do fit in this interval. And if I add 2k pi over 3, so imagine that instead of putting this in the fraction like this, I put it outside the fraction like this, right? If I add or subtract by that, we notice that this is bigger than the entire interval. It's bigger than pi over 2. So if I add that, I'm necessarily going to be outside the interval. And if I subtract it, I'm also going to be necessarily outside the interval. So these are actually the only two solutions that I have. I don't need to do any plus 2k pi. All right, so my solutions are just the ones in part A, in option number 1, that is. All right, pi over 18 and 5 pi over 18. Okay, that brings us to another tricky topic, which is quadratics that have trigonometric functions in them. Okay, and we call these pseudo-quadratics, which means a quadratic in disguise, where the variable is not x. And on exams, these questions will often require that you use the Pythagorean identity, sin squared plus cos squared equals to 1. So here's an example. I have 2 cos squared x is equal to 3 sin x. I'm going to start by rewriting everything in terms of sine, because I have this cos squared term that I can transform into something sine squared using my identity. So if I take this identity, it means that cos squared of x, or cos squared of theta, is 1 minus sine squared. And I plug that in here. So I get 2 times 1 minus sine squared theta is equal to 3 sin x. Okay, I rearrange that. I get 2 sin squared plus 3 sin minus 2. And I let u is equal to sine x to make my life easier, and I'll notice what I would need to notice a bit better. I'll have 2u squared plus 3u minus 2. Okay, and now I use the quadratic equation. I do negative 3 plus or minus the square root of 3 squared minus 4 times 2 times minus 2. That becomes 9 plus 16, which is 25. So I do minus 3 plus or minus the square root of that is 5. So, and all divided by 4 gives me 1/2 or 2. But here's the thing. Sine of x, which is u, cannot be equal to 2, to minus 2. That's just outside the range. It's always between minus 1 and 1 inclusive. So this is the only value that is actually relevant. All right, and when is sine of x equal to 1 over 2 in this domain? It's when I have x is equal to plus or minus pi over 6, and sorry, not plus or minus. I either have pi over 6 or pi minus pi over 6, which is equal to 5 pi over 6, right? And I could add plus 2k pi to these, but that would be outside of the domain. So these are the only two solutions. Okay, any questions about that? These quadratics can be tricky, but we're going to go over plenty of exam-style problems of these to make sure that it's 100% locked down. Next, as promised, an example. I'm going to give you a solid maybe 4 minutes to try it on your own, and then I'm going to go over the solution with you. Okay, that's time. Let's start solving this. So I have an equation, 2 sin squared x plus 3 cos x is equal to 3. So I have sin and cos in this equation, and I'd like to have only one or the other. And there's not much I can do with the 3 cos x because it's just sitting there, but a sin squared term I can turn into a cos squared term using the fact that sin squared of x is equal to 1 minus cos squared of x. Okay, what does that mean? It means that I have 2 times 1 minus cos squared of x plus 3 cos x is equal to 3. All right, so that makes 2 minus 2 cos squared of x plus 3 cos x minus 3 is equal to 0. If I rearrange everything, negative 2 cos squared x plus 3 cos x minus 1 is equal to 0, okay? And I'm going to change the signs on this to make it all positive, or to make the leading term positive. I prefer to work that way. But I'm also at the same time going to let u is equal to cos of x. So u squared, 2u squared minus 3u plus 1 is equal to 0. And now I can factor this by looking, I have 2 was the first term and 1 is the last term. So I'm looking for a product of 2 and a sum of minus 3. So I can write that as 2u squared minus 2u minus u plus 1 is equal to 0. So 2u times u minus 1 plus, or minus 1 times u minus 1 is equal to 0. And so 2u minus 1 times u minus 1 is equal to 0, which means that u, which is cos of x, is equal to either 1 over 2 or 1, okay? So this gives me two solutions for x. This gives me, the first one is at pi over 3. And the second one is at 2 pi minus pi over 3, which is 5 pi over 3, right? And the second one is when cos of x is equal to 1, which is just when x is equal to 0, because I don't have the inclusive 2 pi here. Otherwise, I would also include 2 pi. So my answers are pi over 3, 5 pi over 3, and 0. To a harder quadratic equation. Oh God, this is ugly. Okay. It is 10 past 10. Yeah. So for the interest of time, I'm going to start this one straight away because I have a lot of higher level content to go over as well. But I have cos of 6x minus 2 sin squared of 3x. Well, hang on, we don't have the double angle identity yet, so we really shouldn't be doing this. I'm still going to show you how to do it, just so that we have done this question, but we haven't actually introduced this identity yet. So remember that I have the identity cos 2x, where cos 2 theta is equal to 1 minus 2 sin squared of theta. All right, in particular. So I can write I can write cos of 6x as 1 minus 2 sin squared of 3x. All right, what do I get if I put that on the left-hand side? Well, I get cos 6x, which is 1 minus 2 sin squared x minus another 2 sin squared x. That's just going to give me 1 minus 4 sin squared x, all right, is equal to 2 cos squared x. Sorry, and it's supposed to be 3x, plus 3 cos 3x plus 2. And there's a question here that says, couldn't we use the Pythagoras identity to get rid of the sine term? We could, but you would still have cos of 6x. But you know what? That would actually be shorter. So maybe I'll do your way. Cos of 6x is equal to 2 times cos squared of 3x plus 2 sin squared of 3x, right? Plus 3 cos 3x plus 2. And these two terms just become 1. So this becomes cos of 6x is equal to, or this becomes 2 times 1, because sin squared plus cos squared is equal to 1. 3 cos 3x plus 5. Okay, and this is a 6x here. And now I use the double identity for cos x. So cos of 6x is equal to 2 cos squared of 3x minus 1. So what do I get? I get 2 cos squared of 3x minus 1 minus 3 cos 3x minus 5 is equal to 0. Okay, let u is equal to cos of 3x, and I get 2u squared minus 3u minus 6 is equal to 0. All right. That's not going to give me nice values, I think. So I'm going to check if there was a mistake there. I'm seeing 4, 2, minus 3, and minus 5. Yeah, there is a mistake. That's not 5, that's 4. 4, and then minus 4, and then minus 5. Okay? And that is much better because it allows me to do this quadratic by factoring, right? I have 2 times 5 is minus 10. That's the product, and a sum of minus 3. So I can do 2u squared minus 5u plus 2u minus 5 is equal to 0. And that's going to give me u times 2u minus 5 plus 1 times 2u minus 5 is equal to 0. All right. What does that give me? It gives me u plus 1 times 2u minus 5 is equal to 0. Or in other words, cos x or cos 3x is equal to minus 1 or 5 over 2. But we have to reject that. That's outside the range of cosine. So I just have cos 3x is equal to minus 1, which means that 3x is going to be equal to, well, cos is minus 1 when I'm at pi over 2 plus 2k pi. So pi over 2 plus 2k pi. If I divide by 3, I get x is equal to pi over 6 plus 2k pi over 3. Cosine is not negative 1 at pi over 2, it's negative 1 at pi. So that's just pi, actually. And this should be pi over 3, pi over 3, pi over 3. And so my solutions are pi over 3. And then if I add 2 pi over 3, that gets me to pi. And if I add 2 pi over 3, again, that gets me to 5 pi over 3. If I add any more 2 pi over 3, I'm going to be outside of the solution domain. So I stop there, and these are my 3 solutions. Okay, now it's time to talk about trig identities. That problem that we just did probably should have been done later, but in any case, let's talk about all these identities that we have. So the first identity, and we've talked about it already, is sin squared theta plus cos squared theta is equal to 1. I'm giving it to you again because it's the most important, and I really want this one to be stuck in your head. Not just the kind of formula that you like, oh, I need to use a trig formula. Let me go look at my booklet and decide which identity I'm going to use. No, it has to be the kind of identity that you know so well that you can be looking at an equation and notice that you can use it even before you start thinking about which one to use. It just has to jump out at you, okay? Next is the double angle identity for sine, okay? And it basically states that sine of 2 theta is 2 sine theta cos of theta. I'm not going to bother proving it. It's a little bit of a waste of time. You can go find a YouTube video that does that if you'd like. But let's say I know that sin of theta is equal to 3 over 5 and cos of theta is equal to minus 4 over 5. Let's find sine of 2 theta, okay? So if I do 2 times sine of theta, so 2 times 3 over 5 times minus 4 over 5, I get negative 24 over 5. That is sine of 2 theta. All right, pretty basic example, but basically just an identity that you can use. We also have a double angle identity for cosine, and this one we have in 3 different forms, and they're all in your booklet, so it's good news. So I have cosine of 2 theta can be written as cos squared of theta minus sine squared of theta, or as 2 cos squared theta minus 1, or as 1 minus 2 sin squared theta. All right, why are there 3? Well, because sin squared theta plus cos squared theta or cos squared theta is equal to 1, I can take this identity and replace either the sine squared or the cos squared with the other one using the Pythagorean identity. So you can get it just in terms of cos or just in terms of sine. Now, which one do you use on an exam? It typically won't matter. If you pick the right one, then you won't have to use the Pythagorean identity again. If you pick the wrong one, then the worst case is that you simply have to use this identity, 20 seconds later, okay? So it's not too big of a deal, but you can sort of be smart and say, okay, if I used this one, that would cancel with that term, so I'm going to use, 2 cos squared minus 1, for example. It just depends on what you have, all right? Let's suppose that I have sine of theta is equal to 3 over 5 and cos of theta is equal to minus 4 over 5. Let's find cos of 2 theta, okay? So I'm going to do cos squared theta minus sin squared theta, so minus 4 over 5 squared minus 3 over 5 squared, that's 16 over 25 minus 9 over 25 is 7 over 25. All right. Now another IB style problem. I'm going to give you 3 minutes to get a head start, and then we'll continue. All right, that is time. Let's go over the solution to this. So in part A, we're trying to show that sin minus cos x squared is equal to 1 minus sin 2x. So let's start with what I have on the left-hand side. I have, if I expand that, I have sin squared of x minus 2 sin x cos of x plus cos squared x. Okay, and what I can do is I recognize that sin squared of x plus cos squared of x is equal to 1. And therefore I have 1. This is all equal to 1 minus 2 sin x cos x. But that is just 2 sin x cos x is just sin 2x. So 1 minus sin 2x. That answers part A. And in part B, we want to find the value using that part A of sin pi over 12 minus cos pi over 12. So how can I use part A? I know that if I did sin pi over 12 minus cos of pi over 12, and I squared it, I should get 1 minus sin of 2 times that, so pi over 6. All right, and sin of pi over 6 is 1 over 2, so this should get me 1 over 2. And therefore, sin of pi over 12 minus cos of pi over 12 should be equal to plus or minus root 2 over 2 if I square root 1 over 2. All right. And the question is, what do I do next? So now I have plus or minus root 2 over 2. Okay. Now, the question is it plus or is it minus? And to think about that, we have to realize that, well, sin pi over 12 is in the first quadrant, so sin and cos are both going to be positive. But pi over 12 is somewhere like here, because pi over 6 is here, which means that cosine, which is the x, is a lot bigger than sine, which is the y. So if I do sine minus cosine of pi over 12, I should get something that's negative. So I should have negative root 2 over 2. And that is my answer. Next, another similar question. First, we want to show a trig identity, and then we want to use that to solve an equation. All right, this is a really common IB question, and I'm just going to sort of start straight away. I'm going to expand both of these in terms of their double angle identity. So I'm going to write cos squared of x minus sin squared of x. That's for cos 2x. And then sin 2x is going to be minus 2 sin x cos of x. And that's all equal to 2 cos of x times, oh, sorry, hang on. I'm trying to show that's equal to, I can't write that it's equal to that. I'm trying to show that it's equal to that right-hand side, okay? How can I do that? I want to try and gather, I want to try and factor out my cos terms. So what I can do is I notice that I have cos squared and then 2 sin cos x. What I'm going to do is I'm going to rewrite this sin squared as 1 minus cos squared. I should have probably used a different double angle, but I didn't know where I was going until now. So cos squared x plus, or so minus 1 minus cos squared x is equal minus 2 sin x cos of x. So I should put left-hand side is equal to that, is equal to that. Okay, and this becomes 2 cos squared x minus 2 sin x cos x minus 1. And now I can factor out 2 cos of x from the first two terms, and I find cos of x minus sin x minus 1. All right, that's part A. And now we're trying to solve the equation cos of 2x minus sin 2x plus sin x minus cos x is equal to minus 1. So I'm trying to solve if I move the sin x and the cos x to the other side, negative 1 plus cos x minus sin x. That's a direct rearrangement of the equation. And I know now that cos of 2x minus sin of 2x is 2 cos of x times cos x minus sin x minus 1. All right, so that's equal to minus 1 plus cos x minus sin x. All right, I remove the minus 1s from both sides. They don't make a difference. And then what do I have? I have 2 cos of x, cos x minus sin x is equal to 1 times cos of x minus sin of x. All right. And therefore, if I if I bring everything to the left-hand side and factor, I get 2 cos of x minus 1 times cos x minus sin of x is equal to 0. And that means that either 2 cos x minus 1 is equal to 0, or cos x minus sin x is equal to 0. So that actually gives me either 2 cos x is equal to 1, or cos x is equal to sin x. And we're looking for 0 less than x less than 2 pi. So this means that cos x is equal to 1 over 2, which is pi over 3 and 5 pi over 3. So pi over 3, 5 pi over 3. All right? And cos x is equal to sin x on the unit circle when tan x is equal to 1. So if sin x is equal to cos x, it's because the x component equals the y component. So we're along that line, which means I have the solutions pi over 4 and 5 pi over 4 for the other one. Okay, pi over 4 and 5 pi over 4. If I add, because the question says to find the sum of the solutions, then I need to add all of these together. So I do pi over 3 plus 5 pi over 3. That's going to give me 2 pi. And then I'm going to add 5 pi over 4 plus 5 plus pi over 4 gives me 6 pi over 4, or 3 pi over 2. And this will all come out to be equal to 6 pi. So 3 pi over 2 plus 4 pi over 2 is equal to 7 pi over 2. That's my final answer. Ooh, now a hard question that combines logs and trig identities. Okay, so I'm told that log base 3 of the square root of 4 minus 3 sin squared x is equal to, or so we're trying to show that that's equal to log base 9 of 4 minus 3 sin squared x. So I'm going to have to use log rules to do this first part, right? So I have over here, I have log base 3 of 4 minus 3 sin squared x to the power of 1 over 2, because that's what a square root is. And using my log rules, that's the same thing as half of log base 3 of 4 minus 3 sin squared x. Okay? And the right-hand side is log base 9 of 4 minus 3 sin squared x. And I can use my log change of base to say that this is log base 3 of 4 minus 3 sin squared x over log base 3 of 9. All right, and that is the same thing as, because log base 3 of 9 is 2, this is half log base 3 of 4 minus 3 sin squared x. Okay, and that means that my left-hand side is equal to my right-hand side, and I have shown what I wanted to show. Okay, because I have the same thing here as I do here. All right, part A complete. Now part B. I'm trying to find the value of tan of x. Okay, so I'm told that the log base 9 of 4 cos x is equal to log base 3 of this whole square root. But I know that the log base 3 of that square root is the log base 9 of this. So I can write log base 9 of 4 cos of x is equal to log base 9 4 minus 3 sin squared of x. All right? I know that. And that means that I can equate to the inside of the logs. I can say that 4 cos of x is equal to 4 minus 3 sin squared of x. All right? That is what I know. And now I can use my trig identity to rewrite sin squared of x. And I'm going to end up with 4 cos of x is equal to 4 minus 3 times 1 minus cos squared of x. Or in other words, 4 cos of x is equal to 4 minus 3 is 1, and then plus 3 cos squared of x. if I let u is equal to cos x, I end up with 3u squared minus 4u plus 1 is equal to 0, which gives me the roots. U is equal to 4 plus or minus the square root of 16. So 16 minus 4 times 3, so minus 12. And that is being divided by 6. So that's going to give me 4 plus or minus 2 over 6. So that's either 1 or 1 over 3. And those are the values of cos of x. And I'm looking for the values of tan of x. I can find tan by doing sine divided by cosine, but first I need to find sine. Okay, so I do that by saying sine squared of x is 1 minus cos squared of x. So it's either, if I do 1 minus 1 squared, it's going to be 0, or it's going to be equal to 1 minus 1 over 3 squared is 8 over 9. And the question is, which is it? Next step is just take the square root of both sides and say sin x is plus or minus, and the square root of 8 over 9 can be written as 2 root 2 over 3. Okay? And is it plus or is it minus? That's the question. Well, we're told that we're in the solution domain 0 less than x less than pi over 2, which means that sine is positive. So I have the plus case. And therefore tan of x is equal to 2 root 2 over 2. 2 root 2 over 3 over 1 over 3 or 0. Okay? But we have to be careful because cos of x equals to 1 is not valid on this domain because I don't have an inclusive inequality. I have an exclusive inequality. So I don't actually have this solution at all. And so all I have is 2 root 2 over 3 divided by 1 over root 3, which is 2 root 2. And that is my answer. So arcsine is the same as sine minus 1. It's just given this fancy name. And to be honest, I'm not 100% sure why we give it a fancy name. I think sine minus 1 is perfectly fine. But we have to remember that the domain of the inverse function is the range of the original function. And the range of the inverse function is the domain of the original function. Okay? But we also have to be very careful because sine of x has a domain of all real numbers. But we know that it does not pass the horizontal line test. And therefore, to find an inverse function for sine, I have to restrict its domain, okay? So that it passes the vertical line test. So that the inverse function passes the vertical line test. And that means that I'm going to have to restrict myself to the interval negative pi over 2 up to pi over 2, okay? And I'll show you why that is. If you imagine that I have a unit circle here, remember that the sine function takes an angle on the unit circle. It takes an angle, and it gives you the value of y. It gives you the y coordinate. Okay? The inverse sine function is going to do the opposite. It's going to take a y value, and it's going to tell you what the angle is. Okay, but here's the thing, if you pay attention, there is two possible angles, at least two possible angles that gave me that matched with this y value. And in fact, I could add plus 2k pi, and I'd find infinitely many possible angles that solve, for example, if I said this is y is equal to root 2 over 2. There are infinitely many possible solutions. And when I take the inverse function, I need to know what value comes out, because a function gives me back one value. So by convention, we've decided that the inverse sine is going to return values in quadrant 1 or 4, so between negative pi over 2 and pi over 2. All right, and it's purely a convention, but it's the one that makes the most sense because you need to have an interval that actually ranges through all the y values, so from negative 1 to 1, so it has to range all of this, but it also should never go through the same y value twice. So I could have, by the way, picked the interval pi over 2 up to 3 pi over 2. That would have worked. I can't draw that. I could have picked this interval over here. But that would have been really weird because the interval from pi over 2 to 3 pi over 2 is a lot less natural. So this is the most sensible domain, but it's not actually anything objective at all. It's purely a convention. And it's important to understand that it's not a significant mathematical fact, but kind of just something that you need to remember, unfortunately. Okay, So what is the function going to look like? Well, if sine, remember, looked something like this, that's what sine looked like on the interval negative pi over 2 up to pi over 2, then I know the inverse function is the reflection in the line y is equal to x. And so that's how I got this graph of arcsine of x. Okay? Something similar for the inverse cosine, except that when I draw the inverse cosine, what I'm essentially doing, the inverse cosine function will take in a value of x and return the angle that gave you that value of x. And we have the same situation here, the same problem of there being two possible angles. And in fact, there's more than two, there's infinitely many, but there's at least two angles here that I can see that give me the same value of x. Which one do I take? We are going to take values that are in this interval, so from 0 up to pi. Another arbitrary restriction, but we have to make it somewhere. So in this case, this is the inverse the angle that I'd be looking for. All right, and its graph, remember, because the cosine graph looks something like it starts at 1 and goes down to 0 at pi over 2, so it does something like this. And then on the other side, it does something, if I keep going, it does something like that. And if I reflect that in the line y is equal to x, you would get the graph that I've drawn here. Okay? The last inverse function we need to know is the arctan function, and it's a lot less common than the arcsine and arccos functions, but it's still important. And for the arctan function, we need to realize that tan, remember, is a function that takes an angle and essentially gives us a slope in the unit circle. Okay, so tan takes a line like this that goes through the origin, and it gives you back an angle. But there's always going to be two possible angles. There's going to be this angle, and there's going to be this angle, or this angle if you want. So there's a lot of different angles. And by convention, we're going to take, again, the angles in the domain negative, in the range negative pi over 2 up to pi over 2. So that's the range of arctan. And you can see that in this graph here, okay? The other kinds of function you need to know are the reciprocal trig functions, which are basically just 1 over the trig functions you already know. So if I do 1 over cosine, that gives me the so-called secant function. 1 over sine gives me so-called cosecant function, and 1 over tan gives me so-called cotangent function, or cot. Now, I think I'm eternally confused as to why the function that's 1 over sine has cos in its abbreviation for cosecant, and the one that has 1 over cosine does not have cos in its abbreviation. I don't really know why they did that, but it gives you an interesting way to remember them, which is to remember that cosecant is the one that doesn't have cosine in it. It's the one that's 1 over sine. And so actually cosecant and secant, I kind of remember them as being backwards, okay? The good news is they're in your formula booklet, so you don't strictly need to remember their definition. Oh, and maybe let's do an example. If I was trying to find the cosecant of pi over 3, well, cosecant is 1 over sine. So cosecant of pi over 3 is 1 over sine of pi over 3, which is root 3 over 2. So it becomes 2 over root 3. And if I rationalize the denominator, that's 2 root 3 over 3. Now, we already have the identity sin squared plus cos squared is equal to 1. If I divide that through by cos squared of theta, I'm going to end up with the identity tan squared of theta plus 1 is equal to sec squared of theta. And if I divide it by sine squared of theta on both sides, I'm going to get the identity 1 plus cot squared of theta is equal to cosecant squared of theta. All right. In particular, this is the identity we're talking about on this slide. It's literally purely a consequence of this identity and then the definition of the secant function. Okay. But let's have a look at a quick example that might show up at the higher level. Show that 1 over 1 plus tan squared is equivalent to cos squared of x. Okay, so let's use our new identity, which says that 1 plus tan squared is sec squared. So I do 1 over sec squared, and 1 over sec is cos of x, so 1 over sec squared is cos squared of x. And like I was saying, we have a very similar identity for 1 plus cot squared, we do the same thing. It's a consequence of the original Pythagorean identity. We've just divided through by sine squared or by cos squared, or in this case, we've divided by sine squared. And we can do a very similar proof. 1 over 1 plus cot squared is 1 over cosecant squared, which is 1 over sin squared. Now, time for our first little higher level IB question. We have an hour and 15 left, and we have, I can't even see because, yeah, we have 7 questions left to do. So I'm probably going to get started on this one straight away. All right. All right, I'm going to get started on solving this question. So I have 3 cot squared theta is equal to 4 cosecant theta plus 1. And because I have cot squared and cosecant, I'm going to use the identity that says 1 plus cot squared, so 1 plus cot squared of theta, or in this case beta, is equal to cosecant squared, okay? Cosecant squared of beta. So I can write cot squared of beta as cosecant squared beta minus 1. So my left-hand side becomes 3 cosecant squared of beta, cosecant squared of beta minus 3. And then if I subtract the right-hand side, minus 4 cosecant beta minus 1 is equal to 0. What do I get? I get, let me let u is equal to cosecant of beta. I get 3u squared minus 4u minus 4 is equal to 0. All right. And that means, using my quadratic equation, that, and actually, can I factor this by hand? Yes, I can. I can factor this. This is 3u squared minus 6u plus 2u minus 4 is equal to 0. So 3u times u minus 2 plus 2 times u minus 2 is equal to 0. So I have 3u plus 2 times u minus 2 is equal to 0. So that would give me u is equal to minus 2 over 3 or 2. But we have to be very, very careful here. We remember that cosecant of beta is 1 over sine of beta. And sine of beta is always smaller than 1, always, or between negative 1 and 1, which means the magnitude of this, or the range of cosecant beta, is negative infinity up to 1, up to minus 1, sorry, exclusive, and then 1 up to infinity. So this is not actually in the range of cosecant beta. So the only possible value of cosecant beta is 2. Cosecant beta equals 2. That is the answer. All right, now the compound angle identities. All right, I have the identities in my formula booklet. Sin of A plus or minus B is equal to sin A cos B plus minus cos A sin B. And cos A plus or minus B is cos A cos B minus plus sin A sin B. What does that minus plus mean? It means that if I do plus here, I do minus here. And if I do minus here, I do plus over here, okay? Whereas in sine A, if I do plus here, I have to do plus here. And same for minus minus. So here's an example. Let's say we're trying to find cos of pi over 12 exactly. So I noticed that pi over 12 can be written as pi over 3 minus pi over 4. So I said cos of pi over 3 minus pi over 4 is equal to, and I use my cos compound angle identity. I say cos of pi over 3 times cos of pi over 4 plus sine of pi over 3 sine of pi over 4. If I evaluate all of those angles, I get half times root 2 over 2 plus root 3 over 2 times root 2 over 2, and that simplifies to root 2 plus root 6 over 4. We also have the tan double angle identity, which says that tan of 2 theta is equal to 2 tan theta divided by 1 minus tan squared theta. And you can actually find this identity using the double angle identity for sine and for cosine, plugging them into the definition of tan of theta and simplifying, and you'll find this. But this is useful. Let's say we're trying to find the value of tan of pi over 8, okay? So let's say that x is equal to tan of pi over 8. This was supposed to be tan of pi over 4. Tan of pi over 4 is, well, pi over 4 is twice pi over 8. So I can say that tan of pi over 4 is, using this formula with tan of theta is equal to, with theta equals pi over 4 or pi over 8, I get tan of pi over 4 equals to 2x divided by 1 minus x squared. That's supposed to be equal to 1 because tan of pi over 4 is 1. So 2x squared plus 2x minus 1 is equal to 0. And that gives me two possible values, -1 plus or minus root 2. And since pi over 8 is in the first quadrant, tan must be positive, and so I have root 2 minus 1 as the value of tan. Okay, another HL question. We only have a few left. I'm going to get started on it, though, in the interest of time. So we're trying to show that 1 plus tan squared over 1 minus tan squared is equal to secant of 2 theta. All right. So let's start by noticing that 1 plus tan squared is the same thing as sec squared, because I have the identity 1 plus tan squared theta is equal to sec squared theta. So I have 1 plus tan squared theta over 1 minus tan squared theta is the same thing as sec squared of theta over 1 minus tan squared of theta. That's the first step. And now, if I use the definition of tan theta is equal to sine theta over cos theta, then I can write this as sec squared theta over 1 minus sine squared theta over cos squared theta. Now, because I have a fraction in the denominator, and I don't like that, I'm going to multiply the top and the bottom by cos squared theta. So I'm going to multiply by cos squared theta over cos squared theta. And that's going to give me, well, cos and sec multiply to give me just 1. So it's going to be 1 over, and then in the denominator, I'm going to have cos squared theta minus sin squared theta. And that is, I recognize that cos squared theta minus sin squared theta is cos of 2 theta. So this is secant of 2 theta. All right, that is part A completed. Now in part B, we are given that tan of pi over 8 is equal to root p plus q. Using the result demonstrated in A, find the values of p and q. All right, so if I say t is equal to tan of pi over 8, and I also identify that secant of 2 times pi over 8 is equal to 1 over cosine pi over 4, which is 2 over root 2. So 2 root 2 over 2. Then I can write that, I can write out this quadratic, which says that, and sorry, why did I say 2 root 2 over 2? 2 root 2 over 2 is just root 2. I can say that 1 plus t squared over 1 minus t squared is equal to root 2. If I expand that, it gives me 1 plus t squared is equal to root 2 times 1 minus t squared. All right, what does that mean? It means that if I gather the terms in t squared, I have t squared times 1 plus root 2, and then I have no terms in t, there's nothing there. I just have that is equal to root 2 minus 1. All right, so if I divide both sides by 1 plus root 2, I get t squared is equal to root 2 minus 1 over 1 plus root 2. Let's rationalize the denominator by multiplying by 1 minus root 2 over 1 minus root 2. And that's going to give me root 2 minus 2 minus 1 plus root 2. All right. Is that correct? Just double checking, because yeah, that's fine. And that will give me, if I divide now, divided by, I'm going to get 1 minus 2, so 1 minus 2. Okay, and I'm running out of little space over here. I'm going to try and keep it as condensed as I can. This gives me 2 root 2 minus 3 over minus 1. So 2 root 3, 2 root 3 minus 3 over minus 1, which is 3 minus 2 root 3. Who said root 2? Yes. Root 2. That was a slip up. It's supposed to be root 2. 3 minus 2 root 2. Okay? And I'm told that tan of pi over 8 is root p plus q. So that means if I square that, I should be getting 3 minus 2 root 2. If I expand that, this gives me p plus 2q root p plus q squared is equal to 3 minus 2 root of 2. So I can say that p plus q squared is equal to 3, and 2q root p is equal to minus 2 root 2. So simplifying that, I notice that I can say q is equal to minus 1 and p is equal to 2, so that I get this. And that indeed will satisfy this equation as well. So these are my answers. Q is equal to minus 1 and p is equal to 2. Tricky question. Tricky question. Now, the compound angle identity for tan tells me that tan of A plus or minus B is equal to tan of A plus or minus tan of B divided by 1 minus plus tan of A tan of B. So here's an example. Let's say we're trying to find tan of 7 pi over 12. 7 pi over 12 is pi over 3 plus pi over 4. So I can say that tan of 7 pi over 12 is tan of pi over 3 plus pi over 4. And then using my identity, that gives me tan of pi over 3 plus tan of pi over 4, all divided by 1 minus tan of pi over 3 times tan of pi over 4. Okay? And that's going to give me, in the numerator, I'm going to get tan of pi over 3 is root 3, tan of pi over 4 is 1. And I multiply those two together, and in the denominator, I get 1 minus root 3. To rationalize that, I'm going to multiply by 1 plus root 3 over 1 plus root 3, and that will simplify down to minus 2 minus root 3. Okay, so here is an example question using that identity. I have tan of theta plus pi over 4 is equal to 3, okay? And tan of theta plus pi over 4, I can write as, so I'm looking for tan of theta plus pi over 4, and I can write that using the identity as tan of theta plus tan of pi over 4, all divided by 1 minus tan of theta tan of pi over 4. Okay, so I can say that that's tan of theta plus 1 over 1 minus tan of theta, because tan of pi over 4 is just 1, and that's all equal to 3. Okay, so let me multiply both sides now, and I get tan of theta plus 1 is equal to 3 minus 3 tan theta. So in other words, 4 tan theta is equal to 2, so tan theta is equal to 1 over 2. All right, hence or otherwise, find the exact value of sine 2 theta. Oof, that's a bit annoying. So sine 2 theta is 2 sine theta cos of theta, okay? And let me clear my screen. Sine 2 theta is 2 sine theta cos of theta, all right? And I know that tan theta, which is sine theta over cos theta, is equal to 1 over 2, all right? Which means that if I square both of those, that sine squared of theta over cos squared of theta is equal to 1 over 4. And I'm squaring because I want to use my Pythagorean identity, sin squared plus cos squared is equal to 1. And I can only do that if I have sine squared and cos squared. All right? So then I'm going to write that sine squared, this is tan of theta, and this is tan squared of theta, okay, is equal to that. And I can write this now as 1 minus cos squared theta over cos squared of theta. All right, and that's all equal to 1 over 4. Or in other words, cross multiplying, I get 4 minus 4 cos squared of theta is equal to cos squared of theta, which means that cos squared of theta is equal to 4 over 5, right? And that's very handy because that means that sin squared of theta is equal to 1 over 5 if I do 1 minus that. And I'm in, which quadrant am I in? I'm in the first quadrant, so both are positive. So cos theta is equal to 2 over root 5. Sin theta is equal to 1 over root 5. And therefore, sin 2 theta is equal to 2 times 1 times the other. So 2 times 2 times 1 over 5 is equal to 4 over 5. All right, and that is part B done. All right, here's a nasty, nasty, difficult question that says in part A to show that arctan of 1 over 3 plus arctan of 1 over 7 is equal to arctan of 1 over n, and write down the value of n. So what I'm going to do is I'm going to write that A is equal to arctan of 1 over 3 and B is equal to arctan of 1 over 7. All right, and I care about the sum of these two things, and that tells me I should maybe be using a tan compound angle identity because I have arctan here. So if I do tan of A plus B, I'm going to get, according to the formula, tan of A plus tan of B divided by 1 minus tan A tan of B. All right, and because tan A is just the arctan of 1 over 3, then tan of A is equal to 1 over 3, and tan of B is equal to 1 over 7. So what does this become? I can write this as 1 over 3 plus 1 over 7 over 1 minus 1 over 21. And I don't like having fractions in my denominator, so I'm going to multiply by 21 over 21. And I'm going to get 7 plus 3 over 21 minus 1. And that gives me 10 over 20, which is equal to 1 over 2. Okay? Now, that means that tan of A plus B is equal to 1 over 2. Okay? Which means that A plus B is equal to arctan of 1 over 2. Yeah? And this is valid, by the way, because I know that A plus B are going to be in the range negative pi over 2 up to pi over 2 because 1 over 3 and 1 over 7 are both less than 1. So arctan 1 over 3 and arctan 1 over 7 are less than pi over 4, but still positive. So when I add them together, I'm still going to be in the first quadrant. So there's no issue with taking the inverse tan of both sides. That's totally valid. All right, and that means that n is equal to 2 is the result that I'm supposed to find in part A. All right, and now it says hence or otherwise, find the exact value of theta, which is equal to 2 arctan of 1 over 3 plus arctan of 1 over 7. All right, so I know that arctan of 1 over 3 plus arctan of 1 over 7 is equal to arctan of 1 over 2, which means that this theta now, I have 2 arctans of 1 over 3 and 1 arctan of 1 over 7. So this becomes arctan of 1 over 3 plus all of this, so arctan of 1 over 2. All right. And now, if I take tan of both sides, I can say that tan of theta is equal to, I use the double angle formula again, I'm going to have 1 over 3 tan of the first thing plus tan of the second thing, so 1 over 2, divided by 1 minus the product of the tans, so 1 over 3 times 1 over 2. I'm going to multiply the top and bottom by 6 to make my life easier, and I'm going to get 2 plus 3 over 6 minus 1 is 6 over 5. Okay, and there's a slight mistake there. Yeah, the numerator is not 6, that's 5. 5. All right, so that's equal to 1. So tan of theta is equal to 1, and both 1 over 3 and arctan of 1 over 3 and arctan of 1 over 2 are less than pi over 4 because 1 over 2 and 1 over 3 are less than 1. That means that I can take the inverse tan of both sides and say tan theta is equal to arctan of 1, which is equal to pi over 4. Right, that's a really tricky question. It was something like this kind of was on the exams before, but boy is it challenging. We have a question. What was the condition under which we can take the arctan? Yeah, good question. So if I know, let me go back. If I have something that says tan of let's say alpha is equal to tan of beta. I want to show you an example that tan of 5 pi over 4 is equal to tan of 3 pi over 4, or of pi over 4, sorry. That doesn't mean that 3 pi over 4, sorry, that 5 pi over 4 is equal to pi over 4. And that is because tan is a periodic function. So it doesn't pass the horizontal line test, which is why when I talked about the domain and range of arctan, I had to restrict its domain and its range. And remember we said that arctan was going to be in the range negative pi over 2 up to pi over 2. So long as the angles that are inside of the tans are inside of this range, then I know that arctan is going to give me back exactly that angle. Otherwise, it's going to give me an angle that's equivalent, that has the same value of tan, but isn't actually the same angle. And I know that the angle theta is in that range because just by thinking about the unit circle, I'm looking for, the range I'm restricted to is this range here. And 1 over 3 is kind of somewhere here, and 1 over 2 is kind of somewhere here. They're both less than pi over 4. So when I add them together, at most they're going to be like, here or something. So they stay in the range. Okay, that's a good question. Okay, this is the last question of the day. It's a question that combines, triangle rules. So in this case, the cosine rule, but also trig identities. Okay. So we are told that the equation 4 sin squared theta plus 2 sin theta minus 1 has a solution theta is equal to 18 degrees. And we want to find the value of cos of 162 degrees. All right, what does that mean? Let's think about this equation. Let's say u is equal to sin squared of theta. All right. That means that 4u squared plus 2u minus 1 is equal to 0 has the roots u is equal to minus 2 plus or minus the square root of, in this case, it's going to be b squared is 4 plus 16 all divided by 8, 2 times the 4. So this gives me minus 2, and then plus or minus square root of 20 is plus or minus 2 root 5 over 8, or in other words, minus 1 plus or minus root 5 over 4. Okay, and I know that sine, the 18 degrees is a solution, so that sine of 18 degrees has to be one of these. Okay, and sine of 18 degrees is positive, so sine of 18 degrees is equal to root 5 minus 1 over 4. All right, and how do I find the value of cosine of 18 degrees? Well, first I use the fact that sin squared theta plus cos squared theta is equal to 1. So I say, if I plug everything in, I'm going to get 25 minus 2 root 5 plus 1 over 16 plus cos squared theta is equal to 1. Okay. And that's going to give me cos squared theta is going to be 16 over 16, then minus 26. So 2 root 5 minus 10 should be minus 10. Hang on, I'm just double checking my work. Oh, it should not be 25. This should be 5. 5. So that's going to give me 6. 6 minus 2 root 5 over 16, and I'm subtracting that on the right-hand side. It's going to give me 2 root 5 plus 10 over 16. Or in other words, cos of 18 degrees is equal to the square root
of 10 plus 2 root 5 over 4. Okay, and I know it's positive because 18 degrees is in the first quadrant. And then cos of 162 degrees is cos of 180 degrees minus 18 degrees, which is equal to negative cosine. When I reflect it in the line y is equal to 0, I get negative cosine. So this should be negative 10 plus 2 root 5 under a square root all over 4. And that is the answer to part A. Kind of nasty, kind of nasty. So I'm going to write that over here because we're going to need it. Minus 10 plus 2 root 5 over 4, and this is being square rooted. Okay, let me clear my screen, and we will continue with part B. Now in part B, we're trying to find the value of cos of 9 pi over 5 using what we just found. So what is 9 pi over 5? Well, let's think about it. 9 pi over 5, what is the 162 degrees? 162 is 180 degrees minus 18 degrees, which is equal to pi minus a tenth of that, so minus pi over 10. So this is 9 pi over 10 radians. So 9 pi over 5 is equal to 2 times 9 pi over 10. Okay? And therefore, cos of 9 pi over 5, using my double angle identity, is going to be 2 cos squared 9 pi over 10, or I'm going to write it in degrees, actually, of 162 degrees minus 1. And we wrote that this was minus root of 10 plus 2 root 5 over 4. So let us plug that in, okay? If I plug that in and I square it, I'm going to get 2 times 10 plus 2 root 5 over 16 minus 1. Okay, what does that give me? It's going to give me 10 plus 2 root 5 over 8. 10 plus 2 root 5 over 8, and then minus 8 for the minus 1. So this gives me 2 plus 2 root of 5 over 8, or in other words, 1, shouldn't be a minus there, should be 1 plus the square root of 5 all over 4. Okay, and that's the answer to part B. Now we're looking at part C, and we're trying to find the length BC in the form square root of A plus B root C all square rooted. Okay, so I have a triangle with a side length of 5, a side length of 6, and the angle 4 pi over 5 there in the middle. All right, so how am I going to do this? I'm going to use the cosine rule, which says that the length CB squared is equal to AC squared plus AB squared minus 2 AC times AB cosine of A. Okay, so in other words, it's equal to, if I do AC squared, it's 25 plus 36 minus 2 times 5 is 10, so 10 times 6 is 60, so minus 60 cosine of 4 pi over 5. All right, now what does 4 pi over 5 have to do with cos of 9 pi over 5? Well, cos of 9 pi over 5 is equal to cos of pi plus 4 pi over 5, which means that cos of 4 pi over 5 is going to be negative what we found for cos of 9 pi over 5. So I can write that and I can plug that in, so I can say that this is going to be 25 plus 36 is going to give me 61, then minus 60, it's going to become plus because minus 60 times 1 plus root 5 over 4. Or in other words, the 60 times 1 over 4 is 15, so 61 plus 15 is 76, and then plus 15 root 5. And that is going to give me CB squared plus 15 root 5.
Okay. And now all I have to do is take the square root of both sides to find CB is equal to the root of 76 plus 15 root 5. Okay, and that is the answer to C. And we have a question here. I'm sorry, how did you get 76? Yeah, good question. Let me add a step. 61 plus 15 times 1 plus root 5. So I did 61 plus 15, and then plus 15 root 5. I shouldn't have skipped that step. Okay, I'm going to let you guys decide in the chat. If anyone wants to do this bonus part, the hint I will give you is to find the area of the triangle using area is equal to half AB sine of C, and then realize that the shortest distance between the sides CB and A is the height of the triangle. Okay, so if I were to take the length CB times the height divided by 2, I should get the same area as if I do this. Okay, and it gives you a nasty, nasty answer, which is why I don't really want to do it on the screen right now. Okay?